little bit more practice doing Atwood's machines. I'm going to do these using the shortcut method. And these two right here are exactly the same, really, as the ones that we did in Atwood's practice 1. Different numbers, but looks like we borrowed the masses here from the number 2 in the last sheet. And for this last one, because this is one that's on an angle, I'm going to do this one both ways, so you can see that. All right, that's my plan. If you would like to, if you prefer doing it that longer way, where you write out the unbalanced force equation for each one of the masses, and you want to see what that looks like for these, you just go back and look at the video for Atwood's practice 1, and just use different numbers. All right. So for part A, we want to make force diagrams for these. I'm going to do that right here for big M and little m. So for big M, I always just throw down that gravity first. So the force of gravity on this big mass M from the entire Earth is going to be 100 newtons. The mass times 10. There'll be a support force on that. And sorry, dang it, I should have told you here that there is no friction. I hope you just assumed that, because we don't, you don't have any information about that, so wouldn't be able to do the problem. The normal force on the big mass M from the table is also 100 newtons. How do I know that? Because there's no motion up down here, so those must be balanced. And then we have our tension force. It's not mine, it's ours. Force of tension on the big M from the string. Don't know what that's equal to. And move over a little bit for this. Force of gravity on the little mass M from the entire Earth is 50. Mass times 10. And when this is released, this is going to accelerate down, which means that down must be the winning direction. And so that means that the tension force must be smaller. It must be losing to gravity. So the force of tension on little m from the string. Okay, so in the shortcut method, we're going to say, okay, what is the unbalanced force, but the total unbalanced force on the system? Total unbalanced force is equal to total mass times acceleration. They both have the same acceleration, so there's no, like, we wouldn't say total acceleration, because this and this, because they're connected with the string, have the same acceleration. This is part A, by the way. This is B. So what's the total unbalanced force? Well, the tension force, it cancels out within the system every time. And so the other forces on this are not in the direction of motion. So they're not playing in the winners-losers game, right? Those two things are balanced and cancel each other out. This cancels out with this, and so this is the only unbalanced force. So the total unbalanced force is the force of gravity on the small m. And sorry, I usually just drop that when I start doing my math. M total, so I guess at this level of the equation I'll write big M plus little m times A. Now plug in some numbers. That's 50. M plus m is 15. And that's going to give me an acceleration of 3.3 meters per second squared. Okay. What about the tension? Determine the tension. How would you do that? Well, to determine the tension, you have to go back and write the equation for one block or the other one or the other. So here, if I do the unbalanced force on the big block M, that's equal to big block M times its acceleration. And the only unbalanced force on this block is that force of tension. and I know what the mass of the big block is. It's 10. And I know what the acceleration is because I just found it. So the tension's 33 newtons. You might be wondering to yourself, well, what if I use this one, Mr. McGrath? You could do that too. And just to show you that you get the same answer, do that real quick for you. So if you had chosen the other one, or if you want, you could also do them both, and then if you get the same answer, you can feel awfully good about yourself that you got the right answer. So here, what about the unbalanced force on the little m? That's equal to little m times a. Well, here we have 50 newtons, that's winner minus loser, is equal to the little mass is 5 times the acceleration is 3.3. So let's see what we get there. If we do some baby algebra, 50 minus, what's 5 times 3.3? I think that's, let's see, 5 times 3.3. I suppose it must be 16.7, right? 5 times 3.3 is 16.5 equals force of tension, and then I do the math here, and I'm going to get, if I round to the nearest newton, I get 33. So you get the same answer either way. Doesn't matter which one you use. So you can use either one, or you can do both if you want that good feeling, knowing that you did it right. Okay. Number 2, force diagrams for these. So this one's bigger, so going to accelerate this way. This is going to accelerate that way. So here, that means I've got the force of gravity on big M from the entire Earth is 1 times 10 is 10. And I know that that's winning because this is going to accelerate down. So that means that force of tension must be smaller. So I don't know what that's equal to. I'm not going to write the equal sign. That's for big M. For little m, I've got the force of gravity on little m from the entire Earth is 0.85 times 10 is 8.5 newtons. And this one's going to accelerate up, so the force of tension on this one is winning. Little m from the string. And that is the same string, so those tension forces are equal. Okay, that's part A. Part B, determine the acceleration of the masses. So the shortcut method, unbalanced force total is equal to mass total times acceleration. So what's the total unbalanced force? Well, these two things are equal to each other, and they're going to cancel out inside the system. If you're looking at, but they're both up, how could they cancel out? But they're going over a pulley, right? So the redirect, the motion is this way on this side and the other way. So here the tension's losing, here it's winning. So they do cancel each other out. So what do we have here? This is winning, and this is fighting against it, pulling the other way against. So the gravitational force for this one is in the same direction as motion, and the gravitational force for this one is in the opposite direction of motion. So winner, loser. It's always going to be the same like that for an Atwood's machine. So let's see, that's force of gravity on the big one minus a force of gravity on the little one. That's equal to mass total times acceleration. So let's do the math. Or let's plug in some numbers anyway, then we'll do the math. Total mass, 1.85 times A. So looks like the acceleration is going to be 1.5 divided by 1.85, which is about 0.81, my calculator is telling me. All right, how do you find the tension? Well, you got to pick one of these. And I'm just going to do 1 this time. You can try doing it with the other one if you want, or maybe you did do it with the other one. If you haven't tried that yet, and you're watching this, but you haven't actually attempted part C, or you couldn't get to the answer, you should pause the video here and take over. I'm going to use this. So the unbalanced force on the big M is equal to the force of gravity on big M, winning, minus the force of tension, losing. Now, unbalanced force is equal to mass times acceleration. So the mass of the big one is 1 times the acceleration is 0.81. Is equal to the force of gravity on the big one, which is 10, minus the force of tension. So some baby algebra here. Find a freshman walking around the hallways and pay them 25 cents to do your algebra for you. That's called outsourcing. Minus 0.81. Oh, I didn't need a calculator for that. That was lazy. So I had 9.19 about. I could say 9.2 newtons, something like that. If you did it with this one, you would get the same answer, or something that would round to the same thing. All right, on a ramp. What do we do? Well, when we make force diagrams for things on ramps, the first thing we have to do is sketch a dotted line that represents that ramp. There's my object, and then drop gravity straight down, force of gravity on big M from the entire Earth would be, big M is 3 kilograms, so that'd be 30 newtons right there. Now everything else that we do is going to be in line with our axes here. So first thing, just going to go ahead and do the X, Y of the gravitational force, and my 30-degree angle is going to be down here. If you make an effort to make this look not like 45 and 45, then the smaller angle will be the smaller angle. In other words, if you have an angle that's less than 45, it's going to go in the smaller corner of your triangle. All right, what else we got? Now, this block is not experiencing any motion in this direction, so this must be equal to this support force. That's the normal force on big M from the ramp, let's call it. And there's a tension force. And I'm being told here that this is being pulled up the ramp, so that must be winning. Is it possible that the block could be sliding down the ramp this way? Sure. If it's heavy enough, like more heavy enough than that one, that could happen. But here we are being told it's being pulled up the ramp. So force of tension on big M from the string. All right. Now, here's the thing. I can do a little bit of trigonometry here. I know that this is the side here that is adjacent to the 30. So 30 times the cosine of 30. 30, that's the mass of the block, times the cosine of 30. Just going to make sure that I'm in degree mode. I am. That's about 26 newtons. Right, we're breaking this 30 into the two parts, and then this is the sine component. So this will be 30 times the sine opposite of 30. So 30 times the sine of 30 is 15, because the sine of 30 is 1/2. So I have that and that. And then we have that those two are equal, so that must be also 26. Okay, there's my force diagram for big M. How about for little m? Well, little m's the same as it always is. If this is being pulled up the ramp, then that means this is accelerating down, which means that down is the winning direction. So the force of gravity on little m from the entire Earth, which is its mass times 10, must be winning versus the force of tension on little m from the string. How do we know that this is winning? Because we were told that it's being pulled up the ramp. Okay, now there's only one string, so that must be equal to that. And that's it. That's all that's acting on this one. Okay, so I'm going to do this one the long way and the short way, since this is the first. We didn't see one of these on the last Atwood's Practice 1. So let's do the long way first. So that's the way, the long way means write a Newton's second law unbalanced force equation for each block. So the unbalanced force on the big block, m, is equal to the big block m times acceleration. Unbalanced force here, this is the direction of motion here. So I do have a winner and a loser. So force of tension minus, and before I put the 15 in there, I might want to remind myself or communicate to other humans that where did this come from? It's the force of gravity times the sine of 30. It's the sine component of that. It's 15. I'm going to put that in a second, so I'm not going to bust you if you put the 15 there, but that's where it came from, and it's nice to see that for anybody who's paying attention. Okay, so force of tension, I don't know what that is. 15, I do know that. And the mass of the big one is 3. And don't know the acceleration yet. So that is the unbalanced force equation for big M. For little m, got the unbalanced force on little m is equal to little m times A. For little m, I've got this gravity, force of gravity on little m is winning, minus the force of tension is losing. Force of gravity on little m is 25. Don't know what the force of tension is. Mass 2.5 times A. All right. Now we add the two equations together, expecting that the tension force is going to cancel out. Plus Ft minus Ft, those cancel. So I get 25 minus 15. And then I add these together. That's 3 plus 2.5 is 5.5. So the acceleration is 1.82. That's how you do that. That's part B. Determine the tension in the string. How do we do that? Well, you can use either one of these equations that you have here. I'm going to use, geez, it really doesn't matter, does it? Let's just do both real quick so we can confirm. So here, the force of tension would be equal to, if I added the 15 over here, it'd be 3 times 1.82. I'm plugging the 1.82 in here, and then plus the 15. And if I use this equation, add that over to this side and subtract that over, so it would be 25 minus 2.5 times the acceleration. And hopefully you get the same thing both ways that we do it. So 3 times 1.82 plus 15 gives me about 20.5 And then if I do it this way, 25 minus 2.5 times 1.82 is 20.5. So either way. What does the shortcut way look like for this? I'll just show you the beginning of it because it turns into the same math here pretty quick. So if you look at the line of motion here, or also you can just look at all the things that cancel out. This is why another reason why these little tick marks are helpful. This and this cancel out. This and this cancel out. So the only things that are actually in the line of motion and not canceling out are this in the direction of this. So this is winning and this is losing, right? This winning, this losing, because this is going down, this is going up the ramp. So if we do our unbalanced force total equals mass total times acceleration, the total unbalanced force is this force of gravity on little m minus the sine component, force of gravity on big M times the sine of 30 degrees, equals the total mass times the acceleration. That's 25. That's 15. The total mass is 5.5 times acceleration, and then that's just going to bring us to this point of the math, so I won't go any further with that. So those are your options. All right.